So on the next slide, you guys will get an opportunity to use this simulation, but I wanted to talk with you a little bit about it first and point out a couple of things to you that will be important for you to know. So we know that gravity and that interaction between objects in space. So for example, this is showing the sun. This is supposed to be the sun right here. Um, and I'm going to assume that's the Earth. We know it's this interaction between the two and the gravitational pull that's going on there that has something to do with why planets orbit the sun, or why a moon, for example, orbits a planet. So I'm going to start this in motion. Okay. And the first thing I want to point out, and let it go all the way around, is that even though we think of orbits and they're drawn a lot of times as being perfect circles, they're not. Now, some of the planets get very close, but they are not. They are a little bit oval or egg-shaped, and the word we use for that is an ellipse. And so what we want to use this simulation for is to try to understand why they're not perfect circles. And we also want to look for a couple of interesting patterns, okay? All right, so the first thing I want to do is I'm going to turn on these vectors down here. And there's the velocity vector. Now, remember, velocity is not a force, but we have to use a vector because velocity is speed with a direction. And here is the Earth, and just like Mr. Newton said in his first law, if this was the Earth and it's headed on its little way with no other force acting on it, it would like to just keep going in a straight line. There off it would go in this particular direction at whatever speed it is going at. It'd like to just go in a straight line. But the problem is we do have another force acting on it. Here's the sun, and this is showing the sun is pulling on the Earth towards it, right? There's the sun's gravitational force pulling towards it. So even though the Earth would like to just go in a straight line, it is also having this net force of gravity pulling it towards the sun, and it's the combination of those two things that makes it orbit. And I don't know, it kind of glitches up a little bit there and then it gets moving. I'm not sure. Probably my internet, we'll see. So I'll let it go around again. Now, what I want you to notice also is that as it moves around, I want you to watch the size of those arrows. And I want you to also watch for a pattern. When do you see those arrows? And again, that's just my internet, I think. When do you see those arrows get larger? And when do you see them get smaller? What you should see is that when the Earth is closest to the sun, it has the longest arrow. That should make sense to us now. It has the greatest gravitational pull on it because it is closest. And we said distance trumps mass, so we know that it's closer here. And the velocity vector tells me something else. Because the velocity vector is longer here, it also tells me that this is when the Earth is actually speeding up a little bit. So a lot of kids don't realize the Earth is not going at this nice little constant rate. It actually goes closer when it's at a position that is closer to, it actually goes faster when it is at a position that's closer to the sun. Let's watch again. Less gravitational force, it's farther away, slows down a little bit. And now as it gets closer to the sun, gravitational force is actually pulling on it and actually causes it to speed up. NASA calls that a slingshot effect. And we've actually used that. The Apollo 13 astronauts had a problem on their way to the moon and did not get to actually land. And we had to figure out how to bring them back. And what they decided to do was actually have them orbit behind the moon and then use the moon's gravitational force to sort of slingshot them back towards the Earth. And NASA takes advantage of this a lot. So I wanted to show that to you as well. Now, I need to point out something else. And again, this is a little glitchy here. But one thing I want to point out, and I'll try to do it when the arrows are a little bit longer back through here. I'll do that. Okay. Maybe there. That's as good as I can get, guys. I want to point out to you, because we've actually seen this question on a release TCAP item. I want you to notice that the vector that represents gravity is perpendicular to the vector that represents force. And that word perpendicular just means that they are at right angles to each other. I could draw a little 90-degree angle in there, and they are at right angles to each other. So yes, we did see them ask that on a TCAP released item. Now, the word eccentricity just refers to how far away it is from being a circle. So if I move this way over, it turns out that comets have super eccentric orbits. But I'm going to go ahead and start this. You're going to see it change a little bit here. Now watch what happens. Now you can definitely see it's not a circle. Wow, okay. And so comets come from way, way out in what we call the Kuiper belt. And as they make their way in closest to the sun, they definitely speed up, and we see them and then slow down as we go back out. All right, so a couple of things to notice here, right? You have two vectors showing up. We don't put the vector, the sun has a gravitational force on the Earth. The Earth also has a gravitational force back on the sun. That's not drawn in our model here, just to help not confuse the issue too much. But because the sun is so much more massive than the Earth, the sun is not very affected by our gravitational pull on it. But we notice a couple of things about orbital motion. First of all, the reason that things orbit is because we actually have both inertia, that says an object wants to keep going in whatever straight line motion it's normally in. An object in motion wants to stay in motion. And gravity. It's that combination of the two that makes something orbit. The other thing we can look at here is that we see that as the planet gets closest to the sun, it speeds up. And we see that it speeds up because it has more gravitational pull. We're going to need that knowledge in a minute. And then finally, if we kind of pause it at certain points, we can see that we have, not right here, but as we come around, kind of right there. And again, I'm not getting it well, but if you pause it just right, you can see that when it is at its closest, let me see if I can get it. Oh, right there, that we have close to a 90-degree angle right here. All right, so now it'll be your turn to see how you do with and you can, with the simulation, you can mess with some things here and see what all you can get it to do.